Have you ever wondered how a distributed operating system works? Well, it's essentially a type of operating system that runs on a network of interconnected computers, each contributing its resources to create a unified computing environment. Imagine a team of synchronized swimmers, each executing their moves individually, yet all contributing to a harmonious performance. That's a distributed system for you. The operating system spans multiple physical machines, coordinating their activities to provide a seamless and integrated computing experience. It's like having a team of computers all working together, each contributing their unique abilities to achieve a common goal. This impressive feat of coordination and resource management is what makes distributed operating systems so fascinating and powerful. So whether you're a seasoned IT professional or just dipping your toes into the world of computing, understanding distributed systems is a key to unlocking many of the mysteries of modern computing. Now, let's dive deeper into the key characteristics and components of distributed operating systems. Imagine having the power of multiple computers at your fingertips. That's the principle of resource sharing in distributed operating systems. In a distributed system, resources aren't holed up in solitary machines. Instead, they're spread out across a network of interconnected computers, each contributing its own resources to the collective pool. Think of processors, memory, storage devices, and even peripheral devices, all working together in harmony, shared among users and processes on different machines. This shared pool of resources allows for a more efficient use of computing power, enabling tasks to be executed faster and more effectively. It's like having a team of top-notch chefs in a kitchen, each lending their skills to create a sumptuous feast. But how do users interact with these resources without getting overwhelmed by the complexity? That's where transparency comes into play. In a distributed system, complexity is hidden to provide a seamless experience. That's the essence of transparency. It's like a magician's trick, where all the intricate workings are concealed behind the scenes, leaving you with a sense of wonder. In the world of distributed systems, transparency is the magician. It cloaks the complexity of the system, making it appear as a unified, single entity. Imagine multiple computers networked together, each contributing its resources to the whole, yet to the user it feels like they're interacting with just one machine. That's transparency in action. It masks the complexities, such as the location of resources, migration of processes, and the replication of data. It's not about deceiving users, but about simplifying their interactions and enhancing their experience. So, in a nutshell, transparency in distributed systems is all about making the complex appear simple, the distributed appear local, and the multifaceted appear unified. Transparency simplifies user interaction. But what about executing multiple tasks at once? That's where concurrency and parallelism come in. Ever wished you could do multiple things at once? That's exactly what distributed operating systems do with concurrency and parallelism. Imagine a bustling kitchen where several dishes are being prepared simultaneously. That's the essence of concurrency. Multiple tasks are in progress at the same time. In distributed operating systems, different nodes or computers handle different tasks concurrently, making the entire operation more efficient. Now let's talk about parallelism. It's like a team of chefs working together to prepare a single dish. They divide the work among themselves, with each chef handling a specific part of the recipe. This is how parallelism works in distributed operating systems. Tasks are further divided into subtasks and spread across multiple processors. This allows for faster execution and improved system performance. In essence, concurrency and parallelism are about sharing the workload and maximizing efficiency. They're the secret ingredients that make distributed systems so powerful and effective. Concurrency and parallelism allow for efficient task execution. But how do these tasks communicate and coordinate? Let's explore that next. Communication and coordination are the glue that holds a distributed system together. Establishing effective communication channels and coordination mechanisms is vital in distributed operating systems. These mechanisms allow processes running on different nodes to exchange data and coordinate their actions, creating a seamless computing experience. For instance, when a user accesses a file, the system needs to coordinate which node has the file, how it's accessed, and where it's stored. Similarly, in a distributed transaction involving multiple nodes, the system must ensure that all steps of the transaction are executed consistently across all nodes. This coordination is critical for maintaining data integrity and consistency. Moreover, communication and coordination mechanisms support distributed computation, allowing tasks to be divided among multiple nodes for parallel execution. This not only enhances performance but also ensures optimal resource usage. While communication and coordination keep the system running smoothly, what happens when things go wrong? That's where fault tolerance comes in. In a distributed system, even when a part fails, the whole keeps working. That's the power of fault tolerance. Now, imagine a large orchestra where every musician plays a crucial role. If one musician falters, the symphony can still go on. That's the essence of fault tolerance in distributed operating systems. At the heart of this resilience lie techniques like replication and redundancy. Replication is like having understudies for our musicians, ready to take over in a heartbeat. Redundancy, on the other hand, is like having multiple copies of the musical score scattered throughout the orchestra. Either way, the show must go on. But what happens if an error sneaks in, like a wrong note in the symphony? That's where error detection comes in, swiftly identifying the error and isolating it before it can cause further harm. And lastly, there's fault recovery. Like a skilled conductor, the system orchestrates a seamless transition, replacing faulty components without missing a beat. Fault tolerance ensures reliability and availability. But what about when the system needs to grow? That's where scalability comes in. In a world where data is ever growing, distributed operating systems are built to scale. But with great power comes great responsibility, the need for security. Let's dive into the principles of scalability and security in distributed operating systems. These systems are designed to handle the ever-increasing computational demands of our digital age. They achieve this through horizontal scalability, the ability to add more nodes to the network as demand increases. This means that as the workload grows, the system can simply expand by incorporating more machines into the network. This dynamic allocation of resources ensures that the system continues to run smoothly, regardless of the volume of data or the number of users. But as the system scales, so does its vulnerability. The openness and interconnectedness of a distributed environment can leave it exposed to security threats. This is where the second principle comes into play: security. Distributed operating systems have robust security measures in place to protect against these threats. They employ authentication protocols to verify the identity of users and machines. They use encryption to secure data during transmission, preventing unauthorized access. Access control mechanisms regulate who can access what resources, adding another layer of protection. And secure communication protocols ensure that data exchange between nodes is safe and secure. These security measures work together to create a fortress around the system, protecting it from data breaches and other cyber threats. They ensure the integrity, confidentiality, and availability of data, maintaining user trust and system reliability. But it's not just about having these measures in place. It's about continuously monitoring, updating, and enhancing them. As the digital landscape evolves, so too do the threats. Therefore, distributed operating systems must be proactive in their approach to security, always staying one step ahead of potential threats. So, we see that scalability and security are two sides of the same coin in distributed operating systems. They work hand in hand to create a system that is not only capable of handling increasing computational demands, but also robust enough to protect against the ever-evolving landscape of cyber threats. Scalability and security are crucial, but there's one more piece to this puzzle: middleware. Middleware, the unsung hero of distributed systems, creating a bridge between diverse platforms. Middleware is like the conductor of an orchestra, ensuring each instrument, or in this case, each element of a distributed system, plays its part in harmony. It plays a crucial role in distributed operating systems, serving as a layer of abstraction that eases the complexities of distributed computing. It essentially standardizes communication protocols, enabling different software components to interact, even if they're running on diverse platforms. Think of middleware as the universal translator in the world of distributed systems. It interprets and translates requests between different systems, ensuring seamless interoperability. It's like the glue, holding together all the disparate parts, making them work as one unified whole. Moreover, middleware reduces the burden on developers, allowing them to focus on the application's core functionality rather than worrying about the intricate details of inter-system communication. With middleware, we bring together all the elements of a distributed operating system, creating a harmonious and efficient network of computers. So now you know the magic behind distributed operating systems, a symphony of interconnected computers working in harmony. They enable resource sharing, allowing processors, memory, storage devices, and peripherals to be utilized across different machines. They provide transparency, making complex distributed computing appear as a single cohesive entity. They support concurrency and parallelism, optimizing system performance by distributing tasks across multiple processors. Distributed systems are designed with robust communication and coordination mechanisms for seamless data exchange and activity synchronization. They incorporate fault-tolerant features to ensure system reliability and availability. They're built to scale, distributing workloads across nodes and dynamically allocating resources based on demand. Security measures are implemented to safeguard against threats in the interconnected network environment. And lastly, middleware provides a layer of abstraction and standardization for distributed computing services. Distributed operating systems truly are a marvel of modern computing, turning individual computers into a powerful, unified network.